All right, it is time to get into complex and imaginary numbers. But if they're imaginary, how can we deal with them? That was the conversation I had in my head with myself. Anyway, they are imaginary, but they're also very present in our world. It's kind of a weird truth. But so we are going to write square roots of negative numbers. That's where imaginary numbers come from. We're going to add, subtract, multiply, and divide complex numbers. And we're going to raise I 2 powers. Now, our little buddy I. It's time to introduce you to him. I is defined as, let me get my, I don't know why it's being all silly. I is a simple little letter, but it is defined as the square root of -1. Now, up until now, we haven't been able to handle these square roots of negative numbers, right? We ignore them. We say, oh, well, that's not a real number, so I can't do it. Well, it's true it is not a real number, but it is a number we can work with, and it's amazing, actually, in real-world applications that these numbers actually do come up. Specifically in electrical engineering and circuits, you see negative square roots all the time. Even though they're imaginary, it does not mean they don't exist. They're numbers that we can work with. So for instance, the reason we have something like this is we know we can take the square root of a positive number, but what if we have like the square root of -9? Well, product rule tells us if we can split this into two different numbers, we can take the square roots of them separately. Well, of course, you know that -9 is equal to -1 times 9. Now, the great thing about that, of course, is that now I can pull this into two separate square roots and say, well, then that's the square root of -1 times the square root of 9. And because we've just defined I here, we now know, well, the square root of -1, that's I, times the square root of 9, which I can't seem to make a dot, which is 3. Now, we never leave our answer in that form. Just like when you have a variable, you don't say x3, you say 3x. So we'll do it the same way here. Let's just switch that around, and we write that answer as 3i. Now, you won't have to go through that whole process every time once you get comfortable with this, but that's basically where I wanted you to see where the I came from. We took that negative number and we split it into -1 times the positive version of that number, and then we were able to handle the square root. Let's see, let me portion something off here and let's do a different one. What if I gave you the, here, this will be a good one. We'll have a negative outside and a negative inside. Negative square root of -24. Well, you know what's going to end up happening here is we're going to have an I anytime you've got a square root when there's a negative under there. So this is going to be negative square root of -1 times 24. So really what we have, let's go ahead and pull that I out, right? So we've got this negative is still here, but the square root of -1 is an I, and we're multiplying that times the square root of 24. Now you can't leave it like that because square root of 24 can be simplified, right? Of course, you remember that by now. So we've got -I times the square root of, well, 4 times 6 is equal to 24. And of course, we know the square root of 4, right? You all remember the square root of 4 is 2? Yes, I hope so. If you don't at this point, you are in trouble. So this would be, I'm going to simplify that. I'm going to write this in a better format in a second, but we've got -I times 2 times the square root of 6. So there's supposed to be a times sign there. Right, because I took the square root of 4, which is 2, and the 6 is still under the square root. So when I go to simplify that, really, how am I going to write that final answer? I'm going to write -2i square root of 6. That's the best way to write that, simplest way to write that. Okay? Yes, it's true. We can do that with weird-looking negative numbers. Okay, let's look at something that you'll find actually quite simple. Complex numbers. Let me introduce you to what a complex number is. A complex number involves an imaginary number, but it also has a real part. A complex number is any number that can be written in this format. Okay, a plus bi, where a and b are real numbers. going to actually write this out. Oh my gosh, I can't write an N. I got ahead of myself. Real numbers. So, in other words, let's just give a few examples. 1 minus 3i. There's an example. That's a complex number. It's got a real part. The a is the real part, and then the negative 3i is the imaginary part. So any complex number is made up of two parts like that. Now, that isn't to say that it'll always have a real part. For instance, just like 5i. Well, that's an imaginary number, but it also can be thought of as a complex number with the real part being 0. We never write 0 plus 5i, but that's what we mean. Okay, so when we add and subtract complex numbers, basically all we're doing is combining like terms. We're going to take the real parts, the real numbers, and add them, and we're going to take the imaginary parts and add them, and it's basically going to be that simple. So for instance, let's say you had 17 plus 4i, there's one complex number, plus 8 minus I. Okay, I wrote these in parentheses just to let you see it that way. But understand, there's nothing going on in these parentheses here that causes you to have to group them that way. There's no operation that we can do. 17 plus 4i, we can't really combine those. Those are not like terms. So really, you can just drop the parentheses at this point. There's nothing being distributed. There's no reason to even pay attention to them. All you really should be paying attention to is, where are my like terms that I can combine? Well, you've got a 17 and an 8. Those can be combined to make 25. And then you have a positive 4i and a negative 1i. Well, 4 minus 1 is 3. So, yes, it really is that simple. When you're adding complex numbers, you're just combining the real parts and the imaginary parts, and there's your answer, 25 plus 3i. Okay, now, that's all well and good, but then if you're subtracting, be careful. Like, for instance, let me give you, let's say you had, squiggly line, first of all, you've got to have a squiggly line, 6i minus 4 plus 3i. Now, you got to be careful here, because, of course, now the parentheses do mean something, because there's a minus sign in front of them. Of course, there's this understood 1 here, right? We usually don't write it, but it's understood. So we're actually distributing a negative 1. So what we really have here is 6i minus 4 minus 3i. We have to apply that minus sign to both terms inside the parentheses. And now combine your like terms. Well, the only ones that will combine are my i's. So rewriting this, I would have negative 4 plus 3i. 6i minus 3i is 3i. And I know what some of you are thinking. Well, could you write it in the other order? Yes, absolutely you could. This is the same thing as 3i minus 4. It's just a standard convention to put the real number part first. So the negative 4 goes first. It doesn't matter. It's the same thing. So the My Math Lab should accept it either way. The order does not matter. So addition and subtraction, pretty straightforward, pretty simple. Now when we get into multiplication, it gets kind of interesting. Of course, you know I have to change colors. Let's start out with something kind of basic, like 5i times 4i. Okay, well, pretty straightforward. If we're going to multiply those, the math itself is not real complicated, right? We can handle the math. 5 times 4 is 20, right? And I times I is I squared. Now, let's think about what that equals. Okay, remember that I'm going to come over here to the side, and I is defined as the square root of negative 1. So what happens if we square that? Well, if we square both sides, if I square both sides, then we have I squared equals negative 1. So you got to pay attention to that. I squared is actually negative 1. So what we really have here is 20 times negative 1, or negative 20. Okay. Okay, so when you're multiplying with these complex numbers, you're going to end up, anytime you have an I squared, that's actually going to become a -1. It's going to change the sign of your answer. And that's where some of these interesting answers come from. That was one kind of example where you had, let's look at another, like the square root of 36 times the square root of -1. Well, of course, we know the square root of 36 is 6, and we know the square root of -1 is I. So that's just 6I. That's pretty straightforward. That's all there is to it. Just making sure we're all clear on the what those problems will look like. Let's not make them more complicated than they need to be. We don't want to do that. You'll also have some where you have distributive property coming into play. So let me come down and let's switch to red, because everyone hates red. Red's so abrasive on your eyes. So makes you feel like you're doing something wrong. 7I times 2 minus 4I. Whoa, what just happened there? Not real sure. Apparently I drug my pen a little bit. So we're going to distribute just like normal. So when I distribute, I have 7I times 2, that's 14I, minus, well, 7 times 4 is 28, and then we have an I times I, which is, of course, I squared. Now be careful here. Again, I squared is -1, so what do we really have here? We have 14I minus 28 times -1, which becomes a positive 28. So really our answer is 14I plus 28. Ta-da! Isn't it magical? I know, it's a little magical. It's okay, be amazed. Now you'll also have a few FOIL problems. I trust that you can handle some FOIL. I hope you can. If you can't, view an example. You know what I'm talking about. I'm talking about like maybe like a 2 plus 3I times a 5 minus 4I, for instance. Something like that. Remember, you can always view an example when you're working these. I'll just do this real quick since I've written it out. We're going to FOIL, right? So 2 times 5 is 10. 2 times -4I is -8I. Inside, 3I times 5 is 15I. And last, I have minus 3 times 4 is 12. I times I is I squared. So again, this I squared, let me highlight it here. This action right here, this I squared is going to become a -1, so that last term actually becomes a plus 12. So now what I really have here is 10. Let's see, minus 8I plus 15I. Combine those like terms, right? Combine those like terms, and that's a positive 7I plus 12. So of course I can combine the 10 and the 12 to have 22 plus 7I. And there is my final answer. Okay, now that's multiplication. Division is maybe even a little funkier, because this is something you don't see too much of, and I think actually I only gave you 1 or 2 of these problems. Let's look at a division example. We'll look at 2 different kinds of division examples. One with square roots on them. So let's say you have the square root of -72 over the square root of -9. -9, that's a bad example, because that could be, I don't want to do that. Let me make something that doesn't work out so beautifully. I don't want it to be that nice and neat for you. Over the square root of let's say 5. Man, I picked numbers again that aren't going to work. That are going to work out too nice. So, I'm having a hard time here. Oh boy. Well, fine. We'll just do 10. Oh, that'll work. 10. Here we go. Okay. So first of all, on top and bottom, if you can draw a 0, which I can't, you know that you're gonna have an I that you're gonna pull out of there, right? So let me just go ahead and do that. This is gonna be I times the square root of 80, and on the bottom I'm going to have I times the square root of 10. That I takes care of the square root of -1. Well, okay, now I have, the i's cancel each other out. I mean, they're gone. I over I, anything over itself is just 1. So now I have the square root of 80 over the square root of 10. Well, we remember from our rules of radicals that we can combine that into one radical, the square root of 80 over 10, which reduces to the square root of 8. And of course you're not done, because you know the square root of 8 is 4 times 2, so that's 2 times the square root of 2. Bam! So that's one kind of multiplication problem you could have. Here's a different kind, or I'm sorry, not multiplication, division. A different kind is really the one that throws people off, like 11 over I. What on earth do you do if you have an I down there in the denominator? Well, luckily, if we multiply I by itself, it cancels itself out. Anytime you want to cancel something out in the denominator, you can that has square roots or i's in it, you can think about the conjugate. The conjugate, never mind. Don't, you know what? Ignore that last sentence. I don't even want to go down that road. There's no reason to make this more complicated than it is, because it's actually fairly straightforward and simple. Let's just multiply by I on top and bottom. Remember that you can always multiply a fraction by the same thing on the top and the bottom without changing its value, right? Yes, of course you can. Well, now on top I have 11I over, remember, what is I times I on the bottom? Well, it's negative 1, right? I times I is negative 1, I squared. So this gives me just negative 11I. There you have it. Negative 11I. If my pen would go away. Negative 11I is our answer, because negative, or 11I divided by negative 1 is negative 11I. Alrighty then. Okay, we've done all 4 operations. We've got one last objective, and that is raising I to different powers. Now there's an interesting pattern that exists when you raise I to different powers. Obviously you know what just I itself is. I to the first is I. And you know that I times I, or I squared, you know that's negative 1. Well, what's I to the third power? Well, think about what I to the third can be broken into. I to the third can be rewritten as I squared times I, right? Of course, because 2 plus 1 is 3. Well, we know I squared is negative 1 times I. So in other words, I to the third is just negative I. Well, now what about, let me go down a little further, what about I to the fourth? Think, what's I to the fourth? Well, again, I to the fourth can be broken into I squared times I squared, right? Because 2 plus 2 is 4. These are just some basic rules of exponents here. Well, and we know that I squared is negative 1, so what we're really doing here is negative 1 times negative 1, or just 1. Now, this is interesting. So, we have I squared is negative 1, I cubed is negative I, and I to the fourth is 1. What about I to the fifth? Well, I to the fifth can be rewritten as I to the fourth times I, right? Right? Of course it can. And I to the fourth is just 1, so we have 1 times I, or I. Interesting! So you're saying I to the fifth is the same as just I to the first. Yes, I am. What about I to the sixth? Well, again, you can see what I'm going to do here. I'm going to keep breaking it down into parts that I know. I to the sixth can be rewritten as I to the fourth, I squared. And I to the fourth is 1, while I squared is negative 1. So 1 times negative 1 is negative 1. If you haven't picked it up yet, there's a pattern that's repeating itself. So, this is really cool with i's. If you don't think it's cool, then I guess you're not a math nerd like me. So, you have this pattern. Every 4 powers of I, it repeats. You've got I, negative 1, negative I, positive 1, and then that pattern repeats. So you go I, negative 1, negative I, 1, and then back to I, negative 1, negative I, 1. That happens over and over and over again. So, what's great about this is, if you have really high powers of I, you can calculate them very quickly. For instance, I to the 10th. I don't have to break that down. I just have to find where in the sequence is it. Divide it by 4 and find its remainder, because we know that every 4 the cycle repeats. If you want to think about it this way, this is kind of a juvenile way of counting, but I'll just for this time I'll do it. I'll start up here with I. We've got 1, 2, 3, 4, and then we go back 5, 6, 7, 8, and then we go back 9, 10. So I to the 10th ends up to be -1. Like I'm saying, all you have to do is divide that exponent by 4. Well, 4 goes into 10 2 times, but how many are left over? 2 are left over. So that tells you that I to the 10th is equivalent to I squared. What about a bigger one like I to the 32nd? Notice 32 is divisible by 4, right? And it's indeed. So I to the 32nd is just the same thing as I to the 4th, which is 1. Every 4 powers of I repeats. In case you're not getting the hang of this yet. I to the 21st. Well, think about it. Divide it by 4. How many are left over after you divide 21 by 4? There's only 1 left over. So this is equivalent to I to the 1st, which is just I. And then what's your other possibility? Yeah, let me give you one other possibility. Let's say you had I to the 59th. What a huge value! Again, divide it by 4. If you divide 59 by 4, you'll find that you have a remainder of 3. So this is equivalent to I cubed, and remember I cubed is just -I. And there's your answers. So anytime you're raising I to some powers, the I part of it is going to be one of 4 answers. Okay, you can have one of these 4 answers back up here. That's all you can have. Now there could be a number accompanying it. For instance, you could have, let's do something like this. You could have 3. Now let's do 2, because I don't want to try to do stuff in my head. It's too big. If I had 2I to the 5th power, let's see. Okay, well 2 to the 5th power is 32. And then I have I to the 5th power also. But I to the 5th is just equal to I. So this is really just 32I. Bam! Okay, I'm going to stop talking and let you practice on the homework. 15 questions on this one, but they go really quickly. All right, done.